Welcome to the video on how to write your lab report for Experiment 9, Introduction to Volumetric Techniques II. In Part A of this experiment, the proper techniques to use a buret will be learned. First, the buret is acclimatized with the solution to be dispensed with the buret. Fill to near the zero mark with the solution to be dispensed. Check for air bubbles in the buret tip and for leaks. If there are no air bubbles or leaks, and the bottom of the meniscus lines up with the buret scale, then read and record the initial buret reading. The video for Experiment 2 shows how to read the buret. Place an Erlenmeyer flask under the buret. Open the stopcock to dispense the solution. Record the final buret reading. The volume of solution delivered into the Erlenmeyer flask is equal to the final buret reading minus the initial buret reading. In Part B of the experiment, 10 milliliters of a known concentration HCl solution will be pipetted into an Erlenmeyer flask. It is titrated by adding NaOH solution from a buret. This titration will be repeated until good results are attained. It may be helpful to review the video on use of volumetric pipette and the video on titration. The aim is to achieve titration volumes to within 0.1 milliliter of each other, to achieve consistent light pink endpoints with each trial, and to achieve an experimental NaOH concentration that is within 1% of the true NaOH concentration. This is an example of what the raw data may look like. The results of 4 titrations shown. Note all the volumes are read to 2 decimal places. The titration volumes used in this and the following examples are just for illustration purposes. Since the concentrations of the acid and base in the lab will be significantly different than in these examples, the actual volumes found in the lab may be significantly different than those shown in this video. The first thing to do is to calculate the volume of titrate NaOH used for each titration. The volume used is the final buret reading minus the initial buret reading. For trial 1, this is 10.38 milliliters minus 0.12 milliliters, which gives 10.26 milliliters of NaOH used in this titration. For trial 2, it is 20.58 milliliters minus 10.38 milliliters to give 10.20 milliliters of NaOH used. For trial 3, 10.03 milliliters of NaOH was used, and trial 4 used 9.99 milliliters of NaOH. Only the good titration should be used to determine the average titration volume. Consistent titration should result in volumes that are within 0.1 milliliters and pale pink transition endpoints. Trials 1 and 2 are within 0.1 milliliter of each other, but both of them are titrated to a darker red color than that which is desired, so they are not ideal candidates to be included in the calculation of the average titration volume. Trials 3 and 4 are also within 0.1 milliliter of each other, and their endpoints are the desired pale pink color. In this example, trials 3 and 4 are used to calculate the average titration volume. The average of 10.03 milliliters and 9.91 milliliters is 10.01 milliliter. When considering which trials to use, remember that errors introduced during pipetting will not show up as a poor color change observed at the titration endpoint. This is another example of what the raw data may look like. The results of the 4 titrations are 15.24 milliliters, 15.39 milliliters, 15.27 milliliters, and 15.21 milliliters of NaOH used. And all of the titrations gave a nice pale pink titration endpoint. Trials 1, 3, and 4 are all within 0.1 milliliter of each other, but trial 2 is outside this range. Perhaps slightly more than 10 milliliters of HCl was erroneously pipetted into the Erlenmeyer flask in this trial. In this case, trials 1, 3, and 4 are used to determine the average titration volume. The average of 15.24 milliliters, 15.27 milliliters, and 15.21 milliliters is 15.24 milliliters. This is another example of what the raw data may look like. The results of the 4 titrations are 15.24 milliliters, 14.52 milliliters, 14.62 milliliters, and 14.42 milliliters of NaOH used. Trial 1 has a red endpoint, and its volume is simply more than the other 3 trials, so trial 1 is discarded. Trials 3 and 4 differ by 0.2 milliliters, but both are within 0.1 milliliter trial 2. Since trial 3 has a darker endpoint, it is discarded. In this case, trials 2 2 and 4 are used to determine the average titration volume. The average of 14.52 and 14.42 is 14.47 milliliters. Using this average titration volume, the percent error of the NaOH concentration can be calculated in the following slides. From slide 6, the concentration of HCl used in the titration is 0.1067 molar. From slide 3, the volume of NaOHCl used in the titration is 10.00 milliliters. From slide 6, the experimental volume of NaOH is 14.47 milliliters. To calculate the experimental NaOH concentration, the balanced titration reaction is needed. In this case, the balanced titration reaction is HCl plus NaOH react to form NaCl and water. Since the reaction is 1 mole of HCl to 1 mole of NaOH, at the equivalence, the moles of NaOH added from the buret must be equal to the moles of HCl initially present in the Erlenmeyer flask. The experimental concentration is calculated by the volume of NaHCl times the concentration of times the mole ratio divided by the volume of NaOH. In this case, the experimental NaOH concentration is 0.07374 molar. Review experiment 3 video to do the percent error calculation. The actual NaOH concentration will be divided by an instructor. In this example, the concentration is assumed to be 0.07423 molar. From slide 7, the experimental concentration is 0.07374. Therefore, the percent error is calculated to be 0.70%. In this example, the percent error is less than 1%. Therefore, the lab objective for titration actually has been achieved. The first lab question has to do with the calculation of the concentration of a solution when a certain mass of a compound is dissolved at a given volume. The expanded roadmap for the mole mass volume particles calculation is a useful place to start. Molarity is the solution's concentration in units per moles per liter, so the mass of compound in grams needs to be converted into the moles of the compound. The molar mass of the compound is the conversion factor needed for this calculation. The volume of the solution must be expressed in liters. Then the molarity is the moles of the compound divided by the volume of the solution. Remember to keep track of significant figures. Consider this sample problem, which is very similar to the lab question. In this case, 50.1084 grams of potassium dichromate is dissolved in enough water to make 250.0 milliliters of solution. Since molarity is moles per liter, the approach is to convert the 50.1084 grams potassium chromate into moles of potassium chromate. The molar mass of potassium chromate is needed to do this. Using the periodic table, the molar mass of potassium dichromate is found to be 294.185 grams per mole. Note the molar mass should have at least the number of significant figures as the mass of the compound. Now the moles of potassium dichromate present be calculated. It is found that 0.17033 moles of potassium dichromate are present. What is the volume of the solution? There are 1,000 milliliters in 1 liter, so 250.0 milliliters equals 0.2500 liters. The molarity of the solution is the 0.17033 moles of potassium chloride divided by the 0.2500 liter, which gives 0.6813 molar potassium dichromate. Remember to watch your significant figures. It may be useful to review the videos on significant figures. The second lab question has to do with calculating the concentration of a solution from titration results. Breaking the problem down like this into a series of steps can be useful. The following steps can be used. The balanced titration reaction must be considered. From this, the mole ratio between the reactants is attained. How many moles of HCl are used? This can be calculated from the concentration of HCl solution and the volume of HCl. By using the mole ratio from the balanced titration reaction, the moles of hydrochloric acid used can be converted into the moles of calcium hydroxide the volume of the calcium hydroxide solution to the liters. Divide the moles of calcium hydroxide by the volume of the calcium hydroxide solution will give the concentration of the calcium hydroxide solution. Remember to watch your significant figures. Consider this sample problem, which is very similar to the lab question. In this case, 115.79 milliliters of a 0.08471 molar sulfuric acid solution is needed to titrate 27.58 milliliters of a potassium hydroxide solution. The balanced titration reaction is 1 mole of sulfuric reacts with 2 moles of potassium hydroxide to give 1 mole of potassium sulfate and 2 moles of water. Note that each mole of sulfuric reacts with 2 moles of potassium hydroxide. The moles of sulfuric acid used can be calculated from the sulfuric acid's concentration and the volume of sulfuric acid used. This gives 0.0098086 moles of sulfuric acid. Using the mole ratio from the balanced titration reaction, the moles of potassium hydroxide initially present is found to be 0.019617 moles. Since there are 1,000 liters in 1 liter, 27.58 milliliters of potassium hydroxide solution is equal to 0.02758 liters of solution. The concentration of potassium hydroxide is then obtained by dividing the moles of potassium hydroxide by the volume of potassium hydroxide solution. The concentration of potassium hydroxide solution is found to be 0.713113 molar. Remember to watch your significant figures. If help is needed, review the significant figure videos. Consult the conclusion writing guide and the lab manual for what should be included in the conclusion. The conclusions include a description of what these terms mean and how they are related to the lab. Write the balanced titration reactions and include the physical states of reactants and products. Summarize what is determined in this experiment. Include the volumes and concentrations of the acids and bases. A table may be useful for this. Comment on the titration technique. When reporting the results, make sure all numbers are reported, the correct number of significant figures, and units are given. This is the end of the video on how to write your lab report for Experiment 9, Introduction to Volumetric Techniques.